In this video, we are going to learn how to draw a ROC curve using SPSS and how to interpret the result of ROC curve to use it for your diagnosis or prognosis research. ROC curve is probably one of the most popular choice of the graph, and we use in diagnosis or prognosis research where the prediction is the main goal of the study. Okay, so using support data, we are going to draw our ROC curve based first only using creatinine level. Okay, and how creatinine level can predict 30-day hospital mortality. Okay, so let's go to SPSS and go analyze, and very last choice of is ROC curve. Okay, and test variable is usually the continuous variable. Test variable is usually a continuous variable and you want to use for prediction. And state variable is states. State variable is the variable which indicates state of actual outcome variable. So for diagnosis study, this would be whether a patient does or does not have the disease. And for prognosis study, and this would be whether the patient did eventually develop the disease. So let's go ahead to click all 4 boxes, and then let's go ahead to click OK. And the value of the state variable, and put 1. So in this case, we coded death as 1, even as 1. And if you use other value, for example 2 for death, and you put 2 here. So SPSS know 2 is an event and any other values are non-event. Okay, and let's click OK. Right. So this is the ROC curve. ROC curves get their name from their development during World War II as a way to tune radar receivers. You wanted to balance sensitivity with specificity. Okay, and so y-axis is sensitivity and x-axis is 1 minus specificity. If it's too sensitive, and the receiver would go off all the time and mistaking flocks of birds and held for German planes. Too specific, and it would miss a flight of German planes, which was even worse. The ROC curve graphs sensitivity against 1 minus specificity, and they are first used in individual diagnostic test studies as a way to identify the optimal cut point for determining when a test is positive or negative. So let me show how you can determine the most optimal cutoff point, and based on continuous creatinine level to predict hospital death. Observe the cutoff level and you predict patient would die, and less of the cutoff and you predict otherwise. Okay, and here is a coordinate of the curve. Okay, so let's look at this, for example. And where the sensitivity is 60.5% and 1 minus specificity is 37.7%, that is this point on ROC curve. And this corresponds to a prediction based on the cutoff of creatinine cutoff of 1.3498. Okay, so if you expect event would occur if the creatinine level is larger than this point. Okay, this is the sensitivity. This is 1 minus specificity. So specificity would be 63%. Okay, so you would imagine each of these data points are corresponding to each different cutoff. So if you would use very low cutoff, so claim events, expect the event if the creatinine is greater than 0.35 and you have sensitivity nearly 100%. So you predict everybody with having events, and specificity is 0 in that case. Okay, and the area under the ROC curve. So the best cutoff point can be chosen based on many criteria, but one of the criteria is you may choose cutoff based on the point where sum of sensitivity and specificity are maximized, and how to get that point. And okay, you draw a diagonal line, and then you get the point where this crosses ROC graph. Okay? So it happened to be actually the point and we chose to begin with. So if you choose 1.34 or 35 as a cutoff to claim, predict patient would have events, then that give the best predictions based on the sum of sensitivity and specificity. But this is a very simple criteria and based merely on the numbers. But your best cutoff should be chosen based on clinical judgment. So some disease, and you shouldn't definitely miss it because it will cause fatal outcome. And then you probably want to test and with a higher sensitivity than higher specificity, and worrying too much about specificity. It shows area under the ROC curve. So good prediction tool, the area under the curve reach closer to 1. Okay. And with a tool which does not do anything better than the random predictions, and you'd expect area under the ROC be 0.5. This significance testing whether this area under the ROC is statistically different from 0.5. So here you could say this tool using creatinine is better than nothing to predict hospital death. And this is a confidence interval, 95% confidence interval for the area under the ROC curve. The ROC curve can be less than 50%. And if your prediction is even worse than the random prediction. Let's look at these 3 ROC curves. The blue line is a prediction made by only creatinine, and the gray line is a prediction made by other variables without creatinine. So those are the variables we included in the larger model. Okay? So using actually these variables which are typically available, and then we say predictable ability is improved, is much better than the creatinine alone. And then if we want to see whether adding creatinine improve predictability, we actually need to do one more ROC curve, which is based on the model include other variables and the creatinine level, which is a green line. So improvement in ROC in green line compared to gray line. So this indicates additive predictability of the creatinine, okay, compared to other available data. And therefore, the ROC curves has been a popular choice of examining predictable ability of a new marker. Although, by looking at only ROC, it is actually very hard to make sense out of what is happening. So there are many methods developed to improve over ROC graph. And one of those graphs are calibration plots. This calibration plots is based on the model including only creatinine alone. And this graph is meant to show how good predictability is, and where prediction is working and where prediction is not working. And to do that, what we did is run the binary logistic regression, and everybody now have a predicted probability from 0 to 1 based on creatinine level, and classify patient into categories based on predicted probability. So this is a group, predicted probability is 0 to 10%. This is a group, predicted probability is 10 to 20%, 20 to 30, 30 to 40, 40 to 50, 50 to 60, 60 to 70. And we didn't have a people with a higher predicted probability, so you don't see 80 and 90% here, but of course they could exist. Within each group specified by the predicted probability, and you simply plot proportion of patient who actually died. So if the prediction is perfect, you would expect this group have about 5%. It's a mean of 0 to 10, so 5%. And this group has 15%, 25, 35, and so on. So the better the predictions, and you'd expect to have these bars as increasing as we predicted, so which is closer to 45-degree line. And as you see, the model with creatinine alone, Hosmer and Lemmershore test indicated poor fit, and the calibration plot is not lining up on the 45-degree line. Let's redo the calibration plot using the larger model, including more variables. So now we have a bar graph much closer to 45-degree line. So Hosmer and Lemmershore test indicate this is a good fit. By looking at calibration plot and what information you can gain that you couldn't gain with ROC graph is, you can see, for example, in this data, the model is, you can see that here, okay, an actual percent of dying is larger than the predicted value. So therefore, in this model, and there is under prediction happening for the patient whose risk is higher. And whereas here, patients with low risk, a model is over predicting if they are under the diagonal line. So those information we couldn't gain by our ROC curve. And there are lots of techniques available to accurately assess additive predictability of new markers or new tests. Those include net reclassification improvement, NRI, and integrated discrimination improvement, IDI.